and today we are exploring parallel computing in Numba, how to speed up your numpy style code on multi-core CPUs without leaving Python. Numba gives us two main ways to do this: automatic parallelization with ngit parallel equals true, and explicit parallel loops with prange. This is a great alternative to OpenMP pragma in C++. We have no GIL bottleneck because we are no Python code. We'll focus on automatic parallelization, showing prange basics from the old doc, and show real speedup with benchmarks in some application codes. So here on the Numba page, you can see that Numba makes Python code fast. Numba is an open source JIT compiler, JIT for just-in-time compiler that translates a subset of Python and NP code into fast machine code. So you can accelerate Python function. Numba translates functions to optimize machine code at runtime using the industry standard LLVM compiler library. Numba compile numerical algorithm in Python can approach the speeds of C or Fortran, which is great news. You don't need to replace the Python interpreter, run a separate compilation step, or even have C++ compiler installed. Just apply one of the Numba descriptors to your Python function, and Numba does the rest, as you can see here, with a simple Monte Carlo P function. You import ngit from Numba. You place this line above your function, and that's all. I have automatic parallelization. So it is built for scientific computing, and also you can use it maybe, for instance, in machine learning, in your notebooks, or on Dask and Spark. You can also do a lot of things like simplify threading, simmed vectorization, and GPU acceleration. Another great way to resume sum it up is this definition by James Weber. When asked what is the purpose of ngit, he said that this short answer is the ngit decorator is telling Numba to compile the decorated function the first time it is called. Numba's big claim to fame is that it is numpy aware, meaning that it can compile code that uses numpy arrays directly. This can greatly speed up numerical code. You can ignore the decorators while running the code, but if you are thinking of modifying the code, you should check to make sure that you are still able to compile the result. And when the user asks why ngit, so why do we have n before JIT, someone else answered that it's a variation of the JIT decorator, standing for just-in-time compilation, but with the no Python option, which is defaulting to true instead of false in later. So make sure that code changes don't accidentally make Numba change the compilation model to something significantly slower. So for today, we're going to focus on this doc. What is automatic parallelization, first of all? Here is a code that will show us the way we can expect with automatic parallelization. We import numpy and numba in all the things we are going to use with numba, so ngit, the set number threads and get number threads function. We have some variables, 100 million, 2 arrays. We have the sequential version of our function, the basic version, and we have the automatic parallel version of our function using parallel equals true. And here we have also ngit. So it is a machine code. but here it will be launched on many threads. So the warm-up is just how we call, which is just calling our functions, timing, the time, and the results. We are showing the effects, the difference between the two functions. So what does it do? Here we can see that the speedup is 14 is a 14 speedup factor on my 32 threads, as you can see. And so when we add parallel equals true to engit here, Numba automatically detects array operations that are embarrassingly parallel, independent elements, that is to say. It fuses them into larger kernels for better cache performance. No changes of code is needed. No changes of code are needed. It is great for numpy-like expression, and it's about the operation, the basic operations, like we're going to see in a, that is to say, the plus, the summation, the multiplication, and so on. So on my machine, we have seen just now that we have a 17.50 speedup factor, just with adding parallel equals true. Numba fuse the multiply, the add, the sin in this function, and the sum into parallel kernels automatically. And this is perfect for array heavy code. So now I would like to talk about the basics of Prange and the privatization rules that we can see here in this documentation, which I find very interesting. So the privatization rules are simple in order of importance. The variables that are operated on with in-place operators are reduction variables. So what is in-place operators? That is exactly this, for instance, plus, minus, multiplication. Those are in-place operators. They specify some reduction. They are written first in the priorities. The variables that are assigned to are private to each thread. The variable will assume the sequentially last value after the loop. This is the equivalent of OpenMP last private clause. So here we have the private variable, and if we execute the code like this, we're gonna have an error here because this is a product reduction, not a sum reduction, and here the variable is not yet initialized. As we are using Prange, the assignment makes it private, and so it needs to be initialized before we can print it. It is not yet available, even though we have here the private that already possesses the value, but we can't access it since it is private to each thread in the loop. And the variables, it comes in second in order of treatment in priority, and at the end the variables that are only read are shared between all threads. And here it is also important to note that although Prange introduces no Python context, it does not actually release the GUI. In addition to not being able to use objects, it is invalid to try to obtain the GUI in the Prange body of a function. This will result in a deadlock. The same parallel equals true also enables explicit loops with Prange like OpenMP parallel 4. I was looking into that because I needed to code Python version of a C code which has a heavy computation part. We'll cover advanced Prange in another video. For now, I just want to show the classic doors. And so, to sum it up, the in-place operators and reduction first in line, the assignment private with equal second, and they will have the last iteration value, and the read-only shared variables are in third position of priority. So it is like this. We have reductions, private and shared in priority order. And we must not use AutoJIT deprecated. Now it is JIT or NJIT, NJIT if you want, the no Python mode. If we launch this code, so now I would like to say also, I would like to speak about the GIL global interpreter lock and give some tips. What is important is that in NoPython, with NJIT, Numba uses native threads, not Python threads, so no GIL release is needed. We have real parallelism. Should we use threads instead of cores? When the parallelism with cores implies a serialization overhead, that can happen sometimes, called picking. So sometimes using threads can be better, especially if you just have a loop with independent data and you don't want to bother putting your data in chunks yourself. For pragma, like in Joglib instance, for pragma OpenMP, it is the simplest equivalent you can find to best reproduce the behavior of your C, C++ code using pragma OpenMP. And for the end, I would like to also a benchmark for Prange, how to use Prange, an example of Prange application. So show the speed. So, and also to compare all the things that we saw before. So the first case scenario is we have a pure Python loop without Numba. So the baseline to show the full speedup we can obtain at the end. Here I also put 32 threads. We have our imports. The first case scenario compiles my function in machine code as we saw with LLVM in bytes. It is hyper very fast. We are in no Python mode. Everything is executed on a single thread. We have no multi-core parallelism either. This is fast thanks to compiling, but we are limited to one CPU core. The GIL global interpreter lock is not a problem because we are in no Python. Numba uses native threads and not Python threads as I have already said it. These natives one don't use the GIL for parallel parts, but here there is not any parallelism anyway. But it's nice to know it. So here in the second scenario, we use NJIT, but in a sequential version as we saw it, but we don't have parallelism. We are not using automatic parallelism, where it's gonna be faster because it is machine code, but we could also use machine code and automatic parallelization as we already explained. So here it activates two things. The parallelization is automatic. Numba analyzes no, here it's for this case. So here, now, it activates two things when we use parallel equals true. The NJIT parallel version with Prange using 32 threads. Here, it activates two things. The parallelization, the automatic parallelization, Numba analyzes my code and detects the operations on numpy arrays that are embarrassingly parallel independent. It merges them in kernels and launches them on many threads, multiple cores. We have the support for Prange. we can use Prange instead of range to force a loop to be parallelized on many threads. It uses many threads when possible, and as many as we want. Numpy launches native threads with OpenMP or TBB, thread building blocks, so we have real CPU parallelism and no kill. So we use our functions, we time them, and we can show the results. Here we just use this line to know whether we are using OpenMP or TBB for the native threads. So here we see that the speedup of ng2s pure is 124 is a 124 speedup factor, and the speedup of Prange versus ngt is times 5 factor, and the threading layer is OMP, not TBB. So we like also to say something about this part here again. So in this part, we have no for loop here. Numba uses automatic parallelization. The operation like a times b and numpy sin plus np sum are detected as parallelizable. Numba launched them on many threads, all our CPU cores if we want. If you don't use parallel equals true, it stays fast thanks to ngit, but it remains on one thread. You can be 4 to 10 times faster if you use more than one thread. For custom loops, I would recommend to use Prange to explicitly tell Numba where to parallelize, and it is, as I already told you, a great way to have an equivalence of pragma OpenMP in your code in Python. So that's exactly what I was looking for in one of my codes, and I'm happy on the with this to implement that in my Python code, which is very fast now. Hope you find it useful. Let you learn something. If it's the case, like, subscribe and comments, and thank you for watching.